Welcome to my newest presentation, Better Quality Through Architecture. Today we're going to talk about why software architecture might well be the best way to improve the overall quality of your software system and might be also the most deciding factor to decide the overall maintainability and longevity of your software system. Well, most software systems end up like the picture we see here. That's a package dependency graph rendered by Sonograph Architect. And what we see are about 50 packages of the open source project Apache Cassandra that form a big cycle group. Meaning from each of those packages you can get to each other package and come back another way. Meaning all those 50 packages basically form one large logical package and cannot be subdivided anymore. So that's a nice visualization of the dreaded big ball of mud. And this is a default outcome for many systems. I'm always joking that you get this outcome for free if you don't have a strategy to fight it. And like in the universe, entropy will always win in software systems unless you fight it by having measures in place that would basically avoid this outcome. Of course, what it does, it makes changes and new features a lot harder to implement. Developers will spend a lot of time trying to understand the code base and will spend very little time actually doing changes. And even if they do changes, they might be very afraid of the outcome of those changes. Maybe they broke something unintentionally because it's very hard to understand all these crisscross dependency going from everywhere to literally everywhere else. Unfortunately, many organizations don't have a real strategy to define and enforce architectural models because it's hard to do. If you're lucky, you have something like a document someplace that describes the architecture, or it's verbally committed from the chief developer to the other developers. But very few organizations actually use real tools for that. There are tools in the market that can help with this. Today we're going to focus on Sonograph Architect, but you could also use tools like ArcUnit and similar to have similar effects. But none of the other tools that we're discussing right now really allow you to define a real architectural model. So this is one of the strengths of Sonograph Architect here. So basically this outcome can only be avoided by using the right tools. What are the symptoms of the big ball of mud? First of all, the dependencies between classes, namespaces, or packages are becoming more and more cyclical. So they're forming cycle groups like the one we saw before, and then those cycle groups grow and merge into bigger and bigger cycle groups. You could justifiably call that code cancer. And now if we use this analog, we could say the cycle groups are tumors and they're growing until they have eaten up most of your software system. That doesn't mean that your software can't work at the end, but it will mean that it is much harder to maintain, to understand, and to keep going for many years. We talk about cycle groups a lot. That's a nice little visualization that shows what a cycle group is. A cycle group basically can be created in a directed graph. We have a directed graph here, and this graph contains two cycle groups, the red one and the gray one. The white nodes are not involved in any cyclic dependencies. And the dependency graphs of those circles can be Java files or C# files, they can be classes, they can be packages or namespaces, whatever you want. As soon as you have defined what the elements are, you can create a dependency graph between them, and then you can find the cycle groups in that graph by using certain graph algorithms. So, how can you avoid the big ball of mud? First of all, you need tools. For example, you need tools to detect those cyclic dependencies. IDEs are not a big help here, and Sonograph Architect is actually designed to do that for you. Then, as soon as you detect the cycle groups, the next step would be to break up larger cycle groups into smaller ones to make sure that they're not growing too big. Basically, cut the tumor before it grows too big. I would recommend that a cycle group should not have more than 5 elements. Some design patterns basically ask for cyclical dependencies, but they should only involve 2 or 3 classes, and that should be it. And ideally, all these classes should be in the same package or namespace. Otherwise, you will also get package or namespace cycles on top of the component cycles. And I highly recommend to avoid package or namespace cycles totally. There shouldn't be any cyclic dependency between packages or namespaces because they're actually really nice to basically overlap with your architecture, and your architecture should be free of cyclic dependencies. The good news is that every cycle can be broken up by the right programming technique. We don't have time to delve into that too much, but an example would be adding an interface to apply Robert C. Martin's dependency inversion principle that mostly works for any cycle. There are also other techniques by basically combining the elements using each other into some higher level or some lower level class. But it helps if you teach your developers how to do that, because many developers actually don't learn that at school. So an even better way to fight the big ball of mud is the use of architectural models. So an architectural model divides your system into smaller and smaller components that can also be nested inside of each other. Then you define clear rules of engagement, means which component can talk to which other component, and everything that is not allowed explicitly is forbidden. It means you basically build firewalls within your software. You clearly define architectural boundaries that can be used for all kinds of things like testing, reusing parts of your software, extracting parts of your software into microservices, whatever you want to do with it. It becomes a lot easier if your system can be modularized and is subdivided into smaller units that are not in a cyclical dependency with each other. To visualize such a model, you can use UML component diagrams, like in this example. Here we see we have subsystems, and they have nested further systems or components inside of them. And then each of those components has incoming and outgoing ports, and you can connect them to each other. As you can see, this is a cycle-free dependency graph between those different components. For example, the search engine has access to the inventory inside of the subsystem warehouse. And it's actually the only one who can use that inventory at this point. Oh no, not true. It can also be used by orders. I can see there's another incoming error there. So SonarGraph comes with an architecture DSL, domain-specific language, that allows you to define UML component diagrams in text form. Once you did this, the tool can detect all places in the code where the model is violated. That also works for the CI build, means you can make your build fail when architecture violations are detected. You can even make your build fail when new architecture violations are detected, basically by using a baseline where you say all these old architecture violations are okay, but as soon as a new one is added, we want to know. And that by itself will already ensure that your system will never end up as a big ball of mud. Provided, of course, your architectural model is detailed enough, because you make a simple model with just one box that doesn't help much. Here's a little example how this architecture DSL looks like. The artifact is basically the box in the architecture diagram. The include statement tells me what is in the box. Everything where presentation is somewhere in the package or namespace name in this example. And then these keywords control allowed dependencies between those different artifacts. For example, the strict keyword means I can just hop one step down. So presentation can talk to business because it's strict. Business can talk to services because it's strict. And services can talk to persistence because it's strict. But also we allow business to talk directly to persistence by using this extra connect statement here. Very simple model. This is how it would look like in another form of visualization, but you get the idea. The language is actually pretty easy to learn. It takes you about 1 to 2 hours to get the basic concepts, and then you can start designing your own architectural models and put it on top of your existing code base. Or you can even start writing this DSL without having any code at all and just preparing your code to be written for this architectural model. Another important factor is a metric-based feedback loop. So, especially coupling metrics can be used to detect problems early. So they are good code cancer detectors, to use that term again. And so when we have a metric feedback loop, we can see when the tumors are growing and do something while it's still easy to fix. Of course, to establish such a feedback loop, you need to measure your systems on a regular basis, ideally during the nightly build. And this can be done by a combination of SonarGraph build, which will upload an XML report with metrics to SonarGraph Enterprise, and that will store it in its database. And we just wrote a new article about this, which explains the default metrics, default KPIs used by Sonograph Enterprise in its default configuration. And the link to this article can be seen on this slide here. It's the newest article on blog.hellotomorrow.com. This is how Sonograph Enterprise looks like. On the left side you see the welcome screen, which basically gives you a list of all your projects. And we configured two metrics to be visible here, maintainability and lines of code. Maintainability level is a special metric that we designed together with our customers to basically measure maintainability of a piece of software. That metric is quite complex but also very powerful. It's a percentage value between 0 and 100. 100 is perfect, 0 is very, very bad. And here it is sorted by this particular value. So the best systems are on top, and the further you scroll down, the more you would see systems that have worse values. You can click on any of those column headers to inverse the sort order, then you could basically have the worst system on top of your list. That would also help. Once you click on one of those systems, you get more details. For example, we get some key metrics here, 2 metric sets, each of 5 metrics each. Those metric sets are described in the article I see below, and once you click on one of those metrics, you can see how the metric changes over time. So you can really detect the trends, which is quite valuable, especially if you understand what these metrics are measuring for you. Sonograph Enterprise allows you to answer questions: which projects grew by the most in the last 30 days, or which projects have deteriorating maintainability. Here's some literature that I recommend, of course, shameless plug, because I'm one of the authors of this book, but don't think I get rich from it. I just am one of 10 authors. I just contributed 1 chapter which explains most of the Sonograph metrics. But there are also many other interesting metrics in here, many other interesting chapters. The other books I also highly recommend. It's from my friend Carola Lilienthal about sustainable software architecture. And this is really down to earth. It looks at a lot of practical assessments that they did over time and what they learned by doing these assessments and what works and what doesn't work. So that's it for the slide part. Now let's jump over to a live demo of Sonograph Architect, where we can demonstrate some of the things we just talked about. So here you can see the welcome screen of Sonograph. I can tell you honestly that this tool has a learning curve. So this page is your friend. It contains a lot of links to documentation, blog articles, and even some tutorial videos that will help you to find your way around with the tool. It's very powerful, but you need a little bit of time to understand the concepts in the tool. But let's jump in what we can do with it. Here I opened an open source system called Gradle. And on the system dashboard, we can already get a lot of information about Gradle. There are some boxes here which give you some overall impression about certain quality aspects of Gradle. For example, in the architecture box, we don't have any numbers. That is because we haven't defined an architectural model for Gradle. But in the structure box, we get a lot of red here. It means we have a lot of cyclic code. About almost 80% of the code base is somehow involved in cyclic dependencies. The red bar stands for larger cycle groups with 6 elements or more, while the yellow bar is for smaller cycle groups between 2 and 5 elements. The green bar means non-cyclic code. So that looks bad at first glance, but the second bar is not as red as the first one. That uses a metric relative entanglement, which is based on another metric called relative cyclicity, which is described in the book and also in the article link that I've given away before. So if you're interested in the details, just look it up. But that tells me that the cycle groups are potentially smaller and we can still do something. If that second red bar would also be up here, we would have very large cycle groups and basically the end stage of code cancer. Of course, ideally you want to have both of those bars as small as possible. So we already know we have some structural issues. We have some early stages of code cancer in here, but it's not catastrophic yet. Then in this box we are measuring the average complexity, basically what percentage of our code base is involved in complex functions or methods. A complex function or method is defined as a function or method that has cyclomatic complexity value of greater than 15 or needs indentation depth of greater than 4. You can manipulate those thresholds if you don't like the built-in ones, but I would recommend sticking with them. And then here you can see the code organization overall. That's where we're looking at God classes, monster classes. We tell you that about 3% of your code base is in large files, and a large file is defined as a file with 1,000 lines of code or more. And on the bottom here we can see how much copy and paste programming we have in that particular system. It's about 1%, so that's not really a big issue. So for Gradle, I think the biggest issue is over here in the structure box, and that's what you see with most systems. That's basically my code cancer thermometer here, the code cancer detector that allows you to find out how much code cancer you already have in your system. Now if I click on this plus bar, I see some extra metrics, some additional metrics. One of them, maintainability level, we mentioned that before, is at 53.4% about. So that's already borderline bad. So everything below 50 is not so good. And this metric is measured as a weighted average of all the modules in the system. So we already know that some modules must have worse values than this, and some modules have better values than this. We'll find out which are our troublemakers very soon. Then propagation cost tells us if I change a random class in Gradle, about 4.4% of all code is affected by this change. So that is relatively reasonable. It's a relatively good value. Average component dependency stands on how many files are affected by a random change. So in Gradle it's about 388 files affected by each change, directly or indirectly, which corresponds to 4.4% of the total number of files, which are down here, 8,810. We also have in this system, we have about 485,000 lines of code. Now, going back here, if you want to see what are the God classes, where are the God classes, you can go to the metrics view, click on the source file level, and click on lines of code. And here we basically changed the threshold to 900 instead of 1000. So with a couple of classes that are larger than our threshold, and basically measuring what percentage of our code is in those last classes. If they're getting too large, it's always a good idea to split them up into smaller classes, because they have the tendency to work like black holes in the universe and attract a lot of dependencies around them. So basically those large classes are also drivers for increasing coupling and therefore making code cancer worse. Back to the dashboard. So if I want to find out what are my most complex routines, I can again go to my metrics view. This time I would go to the routine level and click on, I think we're using modified extended cyclomatic complexity here. And we have some methods that are definitely over the threshold of 15. And then the other metric we're using is indentation depth. So that tells you how deeply you need to nest, and it's not really bad values. But this one method here, for example, has a 6 indentation depth. We could directly jump to the source code from here and have a look. Yeah, and you see that's what's happening here. Lots of indents. So maybe this can be simplified somehow. But back to our main issue. The main issue always is structure and architecture. As the title of this presentation says, quality through architecture, so we have to focus on that structure box. So let's find out what our trouble module is. In this case, again, I go to the metrics view and click on the module level, and then I'm looking at maintainability level, and I'm going to sort it upside down. Now we see, we have one module called dependency management, which is only about 13% maintainability level. That's bad. In total, we have about 5 modules that are below the threshold of 50, so we have to look at them. Now, the interesting question would be, how big are those modules? Are those larger modules or smaller modules? And we can just add a second metric here by doing a command click on a Mac or control click on Windows to add a second metric to that view. And here we can see, unfortunately, our dependency management module is also the biggest module of all of them. So that's not good. We have to look in detail. what's happening here. Typically the cause of those problems are cycle groups inside of those modules. So let's look at what we find under cycle groups here. Sonograph computes cycle groups on 3 different levels here for the system. Module level for components means Java files in that case, package level, and system-wide package level. System-wide package level and module-wide package level is slightly different because it can happen that you have basically the same package in more than one module, and then those packages will be merged, and then we do a cycle analysis, which can lead to much bigger cycle groups. That's why we recommend not to share package names between modules. And there's even a little script that can help you with this. Here is a nice example we can see here. Basically, due to the merging of shared distributed packages, we get a very big virtual cycle group here. It's not really a really big issue in that sense because all those modules are cycle free. It's a Gradle build after all, and Gradle doesn't allow cycles between modules. That would be really bad if we had module cycles. But we get basically virtual module cycles by those distributed packages. If you want to find out which are the distributed packages, we have a little Groovy script that finds that for us, that is delivered together with Sonograph. So let's look for this little script here. It's called distributed packages. We can run that script and it will create us a little tree where we can see the org Gradle internal packages is used in those 5 modules here, and the scopes package is used in those 3 modules, and so on. So that helps you to figure out why do we have these large cycle groups here on the system-wide level. Because if I go to the module-wide level, the package cycle groups are smaller. They're still quite big, but much smaller than almost 500 elements. But I'm mostly interested in the beginning in component cycles, means Java file cycles. And here we see that in our dependency management module, we have the second biggest component cycle group. So that's bad. Let's visualize that cycle group. Now I'm getting a dependency graph of all these cycles. Looks quite pretty and interesting, right? We see different colors. The different colors are related to the direct structural parent. In that case, that would be a package. So this cycle of 69 elements spans over 17 different packages. So basically the component cycle we have here also creates a big package cycle between those 17 packages. But if you look at this closer, you will find out that this graph is somehow split into 2 parts. Basically, you can make a divider line somewhere in between here. And then if you look a little closer, which I of course did before, you will find out that the only way to go from here to down here is over this chain of links. And the cool thing about Sonograph is we can actually simulate our cancer surgery here. Basically, we can make what-if scenario. What happens if I cut that link? I prefer cutting links between different colors. That means I would basically make a cut at a package boundary. Now first let's see what is behind this particular dependency. There's a special view for that called parser dependencies out, and we see we have 3 dependencies going from dependency graph builder to incompatible variant selection exception. If I would double click on one of those links, I could see the line in the code that causes that particular dependency. Now let's make a delete refactoring. It means we're not touching your code with our virtual refactoring. We're just pretending that link is not there anymore. And so I create a new delete refactoring, give this to Paul and write a little comment here that he should do it as soon as possible, and then see what happens to our big cycle here. Haha, that's impressive. So we basically cut this big tumor into two tumors, and basically 3 classes are not cyclic at all anymore. But we have still 2 cycle groups back. A bigger one of about 40 elements and a smaller one of about 20 elements. If I look at this smaller cycle group here, I don't see a low-hanging fruit like I saw before, but maybe it's a matter of perspective. If we change the perspective, maybe we can see something better, something more interesting. So let's try that. First I need to select that particular cycle group, and then I show in exploration view. That's another kind of dependency visualization. And in that case we're using those arcs. The arcs are going counterclockwise. On the left side they go top down, on the right side they go bottom up, and SonarGraph tries to sort those elements in a way that we minimize the upgoing dependencies. So in a cycle-free environment you would only see arcs on the left side. Again, if I click on an arc I can see exactly what dependencies behind us here. We still are attached to the other view, so I have to click on this one here. So this dependency, basically, if I cut this, I can immediately see in that perspective that those 4 elements at least would fall out of the cycle, maybe more, maybe we get lucky. So why not do another refactoring here and give it to Paul. Never again. And this time we hit the jackpot. Nice work, because now from the 20 elements that were all in a big cycle, only 3 remain cyclic. So by just removing that single link, we improved the structure by a lot, which we can also see if you look at here. You see that picture change. We only have a little box here for those 3 remaining cyclic elements. Those are now completely cycle free, and we still have the big box down here. Of course, now we can step further on and try more refactorings to further reduce it, but you see this is a very good way to perform code cancer surgery on a system, because you can simulate those changes before you do them. And that will end up in a to-do list, in our refactoring list here, or in a task list. Both of them show it similar. And I can click on the single refactorings, will tell me exactly what dependency I need to cut. And now if I go into the source code, I will even have little demarkers here associated with these places in the code that need to be touched. Of course, it still requires a smart person to figure out, damn, how do I get rid of that particular dependency? Do I introduce a new interface, or what am I doing to basically stop that from happening? So that little demonstration showed you how you can use SonarGraph basically to detect problematic spots in your software and simulate improving the software. I think we can all agree that it would be a lot harder to do those changes in IDE, because the IDE doesn't help you in visualizing the dependencies as powerful as SonarGraph can do that for you. So it's definitely worth it for you to learn how to use that tool and use it then to improve your software over the long term. For the last part, I opened another system. In that case, we opened SonarGraph itself, or at least a part of SonarGraph, to play around with the architecture DSL a little bit. So a good idea to start with that would be to display the architecture view. And that view can be placed over here. And we see that we have a couple architectural models here, SonarGraph with class, SonarGraph and template, and I'm just going to focus on that particular one. And let's have a look at that. So that's our architecture DSL. You saw the little example in the slideshow before, and this is just like a little bit more complex example. And the cool thing is we can also visualize this using the exploration view. So I'm just say, show me that in exploration view. And I'm putting it next to the DSL text. We can see that we have some architecture violations here, and they're just play violations, because in our real model, of course, we don't have architecture violations, and the build will break if somebody would try to introduce one. But by following those little red X's, I can see we have some upgoing dependencies here and also over here. But let's not get ahead of ourselves. Let's start with something simple. UI Java is one of the artifacts here, and that has, as you can see, 4 outgoing dependencies. If I look at the code over here, UI Java contains everything from a module called standalone Java, which is one of my modules here. And it can talk to the UI interface of core, it can talk to the default interface of UI common, and can talk to the language writer Java UI interface. That 4th dependency here comes from the fact that common is defined as what we call a public artifact, denoted by this green marker here. Means all the siblings defined above it can use it. Now green is good, green arcs basically are depicting allowed dependencies, but we can change that quickly by just commenting that line out here and saving the change. As you can see, those 3 arcs become red immediately because they are now considered to be architecture violations. Let's undo that. Now another thing I talked about was nesting. Here's the first interesting nesting case, because Sonograph looks a little bit like Eclipse because it uses the Eclipse Switch client platform. And of course we only want UI modules to be able to talk to the Eclipse Switch client platform, because our core must be independent from Eclipse, because the core is also used in diverse IDE integrations and also by Sonograph builds, so we cannot have dependencies to Eclipse Switch client platform from the other parts of our software. So what are we doing? We put Eclipse RCP as a nested artifact inside of UI Common here, which means it will become part of the default interface of UI Common. And if you look at this, connect to UI Common means we're connecting to the default interface of UI Common here, basically, which means we can also use Eclipse RCP. And if you look at this, we can see the 3 incoming arcs here. The default interface can be influenced by using certain keywords. For example, if I would use hidden in front of this one here, those arcs would turn red, because now it's not part of the default interface anymore. We basically hide it from the outside world. Also look at the speed of that. We have about 500,000 lines of code here, and it's lightning fast. So the update of the architectural model is pretty fast. Now, another thing that's interesting, if you look at, we call them vertical slices, the 3 language providers, they all have the same internal structure, right? So they have some layers inside of them, command layer, controller layer, and so on. And instead of defining this 3 times, we just say, hey, apply layering, and define the layering in a second architecture description file, which is somewhere over here. And here we see the definition of those layers. We have a command layer that can talk to controller. Controller can talk to persistence because it's strict. Persistence can talk to model because it's strict, but also because model is public. And everybody can talk to foundation because it's public. Then we have this little thing here down called leftovers, a deprecated artifact. That artifact would create an error message as soon as somebody would assign anything to it. It has a pattern that literally matches everything, but nothing gets there because pattern matching goes top down through the file. So we first try with command, then with controller, and so on. If nobody wants an artifact, an element, a component, then it will end up here, and basically that would create an error message as soon as somebody would be matched by this leftovers artifact. It would mean that somebody created a class that doesn't fit in any of our 5 layers here. Okay, so that's cool. Also we see that interface down here. You remember when we say connect to language.c#.ui, that's exactly that interface. And from our 5 layers, we're only exporting 3. To be precise, the command layer, the default interface, the UI interface of model, and the default interface of foundation, which means no direct access to controller or persistence from the outside world. And you can see that here, controller is only used by command. No other incoming dependency going into controller. That's how we want it. We want to basically hide those 2 technical layers from the outside world, coming from the design principle that if the UI wants to do any changes to our model, it has to go over a command. That's why we see the incoming dependencies going into the command layer, and the command layer then can talk to the controller and other things to do what it's supposed to do. And again, we could basically do some simple changes here to make some lines red. For example, if I would just exclude the command layer from being usable from the outside, then this arc over here becomes red, obviously. So that should give you some pretty quick idea what you can use with the DSL. How do you learn the DSL? You go to the welcome page and basically click on this one here, and it will bring you directly to the documentation. And you have to just read that chapter 11 because that contains basically all the information about the architecture DSL. We also on the blog site we have a bunch of articles, and on the website there are also some tutorial videos that show similar things for what I'm showing here, but in a smaller format. Now as a last thing, let's look at the architectural view. That's a view that can be used to basically create an architectural model on an existing code base without having to type DSL. That's basically our interactive architecture modeler, and we just call that now new architecture view, quality through architecture. I'm a little lazy with typing here, admittedly. And then that will create me a new architectural view, which is basically an exploration view that depicts the whole system. The divider lines means everything between the divider lines can be seen as parallel, so they're not using each other. So build only can have dependencies to anything below this divider line, and standalone Java can only have dependencies to anything below this divider line. Also you see that the pluses here have different colors. The darker the plus is, the more classes are behind there. Now in the exploration view you can click in and get more details. Of course it becomes overwhelming pretty quickly, so we don't go too much deeper. But there's one concept here that will help you to work with the overwhelming. Let's assume we have something. You see that becomes really, really big now, and you can get easily lost in here. But most of the time you're just interested in a class and its relationship to the rest of your system. So you can just focus on that particular class and say show me only the incoming and outgoing dependencies of that particular class. So I click on in and out, and I get a limited view that shows me who's using that particular class and what other classes are used by that class. With clear focus I go back here. Now let's start working some simple architectural models. So first of all, I like to assign each of those modules to one architectural artifact. So I click on new, multiple for elements, and make them all relaxed. Relaxed means we allow downgoing dependencies but not upward going dependencies. That will create a new picture. You see the divider lines disappear. Now we have those blue icons that stand for relaxed layers, and now the order is user defined. That's why the divider lines disappear. It's not computed automatically anymore because you are the one who created this. Now you might want to change the order. For example, I could move core up here, and that would create architecture violations because now we have outgoing dependencies. So let's undo that change. For my taste, there's still a little too many top level elements, so maybe I would just combine these elements into a single node here. Call that node build and put it in above the language providers. And ta-da! We already improved the structure a little bit. There are more build elements here, so we have two more which I can drag and drop in here. And now they have the wrong order down here for some reason. I can change that. And now Sonograph of course keeps track of all the operations you did. I can say show an architectural operations view and put that view over here. Sorry, that didn't work. One more time. And here are all the operations I did up to now. And I can even go here and delete an operation, and then it will recompute basically the result of it. Now, out of this, I can already create architecture DSL. You can say, transfer this, please. I don't want to add it to the architecture check quite yet. And that will create a new architecture DSL file for me called quality through architecture, which we will find under architecture here. QTA, there it is. So that was generated for us. You didn't have to type a single character on your keyboard. You already get a basic architecture and can refine it from here. The bad news is once you're working in the DSL itself, you can't go back to this architectural view because the DSL is much more powerful than what you can do in this view. But as a starting point, that's great. Let me show one other use case for that. Another use case would be virtual refactorings, basically moving stuff around, changing package structures. All of that is directly possible in here. For example, I can move a package around by clicking on that thing and then move element, rename element, or do things like this. They're all completely virtual refactorings that don't change the code. but create a to-do list for you. Now let's assume, since core is my biggest module, I know this because it's the darkest box here, maybe I want to split it up into smaller ones. Maybe I want to extract some of the command classes into some new module. So to make sure that my core module gets a little smaller and I maybe can use the command stuff independently from core. So how do I do this? First I create a new artifact called command. And then I put this artifact down here someplace. Oops, I actually want it here. And now how did that happen? No, let's undo. I did something wrong here. Sorry. Undo operation. Okay. Now, create a new artifact. Name that thing command. And insert it down here. Now it's empty. That's why we have a warning marker here. Nothing associated with it. Now let's find the classes I would like to move. Let's assume I just want to use those classes, command and command registry, as a core for my new module. But now if I would just move those two classes, that wouldn't really work. So that shows you why you need Sonograph and can't do that simply in an IDE. I'm just doing that now just for the sake of it. Just say move those two elements into my new module command. And what happens? We get a cycle. Of course, we get a cycle because now those two classes that are in command have still dependencies to other core classes. So that's not really working for us. So in this case, I'm just going to remove that operation again from the operations list here. And now let's do it the right way. And you might have guessed we can use a focus concept for that. I'm clicking on command and command registry. Now I'm clicking on set focus, and now I want outgoing dependencies transitively. Not only the direct outgoing dependencies, but also the indirect outgoing dependencies. And that will create a new focused view where I can only see those two classes and its outgoing dependencies. Now I can move that stuff over. I can say move element. I want to move it into command, but only the shown children due to focus. Now if I can make this a little greater so we can see a list of 27 classes will be moved to my new module. And tada! Now we can clear the focus and mission accomplished. Now we have split the core module into two modules, core and command, no cycles between the modules. And if I save that change, I can also export it again to DSL. And this means we have to overwrite that file. And now if I look back at, you see it changed a little bit. So core is much more complicated now because now we have to list the classes that survived that move operation. And in command we get a list of all the classes that moved into here. So that's basically a to-do list. Now you can go in an IDE and move all these classes into the new module. It's going to be a little bit of work, but you tell me how you would have done this without a tool like Sonograph. I think as an intro that is enough. I hope you'll play around with the tool a little bit and have some fun with it. And of course, you can always reach us directly for questions. Just send an email to support@hellotomorrow.com and we'll be happy to answer all your questions. Thanks a lot for watching and listening, and I wish you a great remaining day.